I want you to imagine yourself at home on the internet, on your computer, on your smart TV, and you're watching a soccer match, or it could be regular cable TV. And you're watching, and the ball is in the air. There it is, a little blurry, but there is the ball in the air. The time into the game is 3 minutes, 59 seconds. And you notice that the ball is 6 meters from the net. There's the ball. And let's say that it's 6 meters from the net. At 4 minutes, your video freezes. And everything is just frozen exactly where it is. The ball is still 6 meters away, but everything is frozen. When reception resumes, 1 second later, you see that the ball is now, well, I've said 3 meters. The ball's moved position, right? It's moved. And you didn't see how it got there. You're not sure how it got there because it froze. So the ball moved from here to there, right? While your image is frozen. Now, what do limits do? You can imagine limits trying to help us in this situation. So limits would say, well, you had this 1 second freeze out, but what if we could make that freeze out shorter? That's like making our h value shorter. What if instead of missing a second, what if we just missed a fraction of a second? And now we see that the ball is 5 meters from the net, and then suddenly it's 4 meters instead of the previous 6 and 3 meters. If we see where the ball is at this time, when it's 4 meters away, and earlier at this time when it's 5 meters away, what is your best guess of the ball's position at 4 minutes? So if we go back to the analogy, the ball is moving during that freeze out. Maybe we would guess that the ball was right here, right? Something like that. Maybe we guess that the ball is right there, somewhere between these two positions. And so limits are going to allow you to estimate an unknown value of a function by using nearby observations. So you're going to use nearby observations to make an inference, or an estimate of the value that you can't actually see. Just like you can't actually see where the ball is at 4 minutes because your stream froze. Now, sometimes limits don't always work. So sometimes we can use this, but other times it doesn't work very well. Not all functions can be sort of have well-behaved limits. And here's an example of a function with where limits doesn't really help us very much. You can imagine that you're watching the TV and the ball is 5 meters from the net. Your stream freezes, and suddenly the ball is 50 meters from the net and moving in the opposite direction. So in that situation, if we've got that kind of a function, these limits aren't going to help us. So limits can help us, but they don't always help us. They can't help us in every single situation. And clearly, in this example, if you're watching a soccer match and the player kicks the ball towards the net, when your stream resumes, the other team has the ball and is going towards the opposite goal. Clearly, you missed something important, and limits aren't going to be able to help us fill in the gaps in that situation. So here's a situation where limits can help us. Take a look at this function. Notice that we've got the natural exponent. And you'll remember from the previous video that the natural exponent is a very special number. I do work in finance and macroeconomics, and the natural exponent is really helpful because it represents continuous compounding. So it shows up a lot in those fields. Now what happens if we're trying to evaluate this function at x is equal to 0? Well, you can see right away that we've got a problem with our denominator. Any number to the exponent 0 is just equal to 1. And that goes back to the real numbers we learned at the very beginning of this course. And we get this sort of absurd, ridiculous kind of answer that we've got 0 divided by 0. And of course, no one on the planet Earth has any idea what that means. And so we say that it is undefined. So we're not sure what the value of this function is when x is equal to 0, but we can use our intuition about limits. And what if x is close to 0 but not equal to 0? What if it was equal to 1? What if it was equal to 0.1? And if we plug numbers in to this function and calculate the value, we can see that we don't know what it is when x is equal to 0, but if we've got x equal to -1, it's 0.63. -1, it was 0.63. At -0.1, it's 0.956. And we're getting closer and closer to what? And closer to 1. We're not getting to exactly 1, but we're getting very close to 1. So if you think of the soccer ball analogy, we can be pretty sure where that soccer ball was when our stream froze. Right, we're getting very, very close to 0. In fact, if we draw this on a diagram, you can see that it looks like a very nice, kind of well-behaved function. The only problem is when it's at x is equal to 0, we don't actually know what the answer is. We don't know what that means. We don't know what 0 divided by 0 is. What is nothing divided by nothing? We don't know. But limits here suggest to us that the value is going to be very, 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 very close to 1. And I'll just point out, notice here that we've got a hollow circle, right? It's a hollow dot. And similar to when we were looking at set theory earlier in the course, when we've got a hollow dot, that means it's not included in our domain or our range. Now, I think it's fairly clear, and I hope that we all agree, that if x is really, really close to 0, f of x is going to be really, really, really close to 1. So looking at the math notation, the limit of f of x as x approaches 0 tends to 1. Tends to 1. So there's an equal sign there. It's tempting. I want to say it equals 1. But to be perfectly accurate, it tends to 1. Putting this in very general terms, let's replace, and maybe I'll write this out to be absolutely clear, because I know that when you're a student and learning this for the first time, it can be hard to work in more conceptual frameworks. So we're going to let A be some placeholder. So let's use the phrase placeholder. A is some number. It's undefined, so we say that A is a placeholder for some number. You probably like questions where it says x is approaching 1, like in our previous example. Here we're going to say, well, let x approach some number A. And as I just mentioned a moment ago, we're actually not totally interested in how fx behaves when x is equal to A. We're interested in how the function behaves when x gets very, 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 very close to A. Now that distinction, in practice isn't going to matter, but conceptually, think about it in the back of your head. We tends towards, x is tending towards A. It's getting really, really close to A, but it's not actually equal to A, even though we write it as being equal.